So this video covers force, work, and potential energy for springs. Let's first talk about Hooke's law, which is the force equation for springs. Let's say that we have a scale attached to a spring, and the spring is in its equilibrium position. This means that it is not stretched or compressed, so the scale should not read any values. Let's say that we then pull on the scale so it stretches out the spring. The scale would then read the value of the force of the spring. The force of the scale on the spring is equal to the spring constant, which is related to the stiffness of the spring, multiplied by the distance the spring is stretched from the equilibrium position, as shown in this diagram. So notice that this force is positive. This is the force that the spring feels when it is being stretched. Therefore, it is going to be pointing in the same direction as the displacement. So the force of the spring on the scale is equal to negative kx. This makes sense because the spring is going to pull the scale back towards the equilibrium position. So these two equations are known as Hooke's law. Now let's discuss potential energy and the work done by a spring. As we discussed in class, the potential energy is the same thing as the amount of work done by some agent to slowly position the object. So in order to find the work done by some agent, we must look at this force versus position graph. And we need to find the area underneath the graph. And if we knew calculus, this would simply be an integral problem. Since this is a triangle, the area is just going to simply equal 1/2 times the length and width, which in this graph is the force and the displacement. And we know that from above, from Hooke's law, that force is equal to kx. So we can substitute this value in, and the equation simplifies into 1/2 kx squared. So as we discussed before, this is also equal to the potential energy because of springs. So let's do an example. You exert a force of 30 newtons to stretch a spring 0.5 meters. What is the spring's spring constant? So we know that in order to find the spring constant, we should use Hooke's law, which states that the force exerted to stretch a spring is equal to the spring constant times the distance stretched. We can then fill in this equation and solve, and we see that the spring constant is 60 Newton meters, and Newton meters is simply just the unit for the spring constant. Next, we must find how much work you did to position this string. To answer this question, we will simply look at our equation that we just found, which is work equals 1/2 kx squared. When we plug in our known values and solve, we see that the work is 7.5 joules. Finally, we could be asked to find the potential energy of the stretched spring. As we mentioned before, the elastic potential energy is just equal to the work an agent must do to position the object. So therefore, the elastic potential energy must also equal 7.5 joules.